essentially in these kind of problems, it's as if we're taking a steel bar, drawing a line on it, and then twisting one side and seeing what happens. And I like to label everything on my picture as well, so I know what my equations mean. Alright, let's see what they give us. We have G is 11.5 times 10 to the 6th psi. Diameter is 1.5 inches. Length equals 54 inches. The torque is 250 pound-feet. Alright, and our objective, we are trying to find maximum shear stress as well as the angle of twist. Now, one thing to clarify, we have the angle of twist, which is usually represented phi. That's how much the end of the bar is rotated. You also have a theta term, which equals phi over L, and usually has units of degrees over feet, for example. And that's just unit twist. Or rather, if I were to cut 1 unit length, how much would that end be twisted, for example? But it's just the end divided by the whole entire length. That's not what we're using in this problem. We're just trying to find how much the end is twisted of this bar. Okay. So if they give us torque and I'm trying to find Tmax, then my thinking is I'm going to start just by writing Tmax equals and finding what equation I know. I just happen to know this equation. Do we know our torque? Yes, we do. Do we have a radius? Well, we have a diameter, so yes, we do. Polar moment of inertia. It's a another formula that you should memorize is for circles. Torque is 250 pound-feet. The radius is the diameter divided by 2, so I put the diameter, which is 1.5 inches, and divide that by 2. Alright, the polar moment of inertia is kind of a nasty equation. It can be quite large at times, but it's pi over 32 times our diameter to the 4th. In this case, our diameter we have, so I can put 1.5 inches to the 4th. Now notice I can't just plug it right into this equation, but just as a side note, I can also write what IP actually is. I have T times D over 2 pi over 32 times D to the 4th. That can be reduced to 16 times T over pi D to the 3rd. This is also a common thing, a common equation to see. So that's another thing you might want to memorize. Or you could just memorize this and plug it in all the time. That's kind of what I do. I want to memorize as few equations as possible and be able to use them skillfully. So, one thing that you should always do is check your units. That's why the last problem I was all stingy on my units. Because notice I have feet here and I have inches here. That's not going to work out so well. So, I have to convert one to the other. Well, I have a whole bunch of inches here, I have 1 foot. So I'm just going to convert my feet to inches here. And my end result is trying to find my tau max, so that's going to end up being PSI, which is a standard unit. You don't want any weird units going on. Okay, so 1 foot over 12 inches. I'm trying to cancel out my feet, so I put my feet on the bottom, my inches on the top. Now I can plug it into my calculator. T89, it kind of shows what I wrote on my paper, and it gave me the answer of 4,527 pounds, which is correct. Alright, so that's the first thing we had to find. I could check that off. Now I'm trying to find my phi, which remembers the angle of twist, not the rate of twist. Okay, now there's a lot of different formulas that are involved with phi, but I'm just going to start with something that I know. I know that phi times r equals gamma times L. So I solved that for phi, but that doesn't really get me very far. Although I know my length and my radius, I don't know my strain, my shear strain. So now I need another formula. Now looking at what we have up here, we have our shear modulus of elasticity, which if we have now that we have our shear stress, we can calculate our shear strain. And that's because of the relationship G equals our shear stress over shear strain. This is just like our regular modulus of elasticity equaling normal stress over normal strain. That's how I remember this formula. Now I could solve this formula for our shear strain, and I get stress over my shear modulus. Now I can plug, if I label this 1 and 2, I sub 2 into 1. I get phi equals tau over G times L over R. And that gives me tau times L over GR. So now I can just plug in my values because I know tau, I know L, I know G, I know R. My tau I just calculated earlier in the last problem. It's 4,527 pounds times length of 54 inches. G was 11.5 times 10 to the 6 psi. And my radius was 1.5 inches divided by 2, since 1.5 inches was the diameter. Plug that into my calculator. Now, what do you think would come out as far as units is concerned? Oh, because that's not pounds. So now my psi cancels out with my other psi, inches cancels with inches. Now that's what I was expecting. It's going to be unitless, which, since we're trying to look at an angle, that means it's in radians. My calculator gave me 0.02834 radians. And for those who are angle challenged, you have, in order to convert it into degrees, I multiply it times 180 degrees over pi radians. Just like I would any unit conversion, the radians cancel out and I'm left with degrees, which then gives me 1.624 degrees. Since this is my final answer, I'm going to put 1.62 degrees and I'll draw my line.